So clearly the direction of the velocity is changing. So therefore, because velocity is changing, it is accelerating. So the direction of the change in direction of velocity implies there's acceleration, which implies there has to be a force, a net force. This relates to when something's in equilibrium, all of those are zero. There's no change in velocity. Acceleration is zero, velocity is zero. Or sorry, scratch that last one. Change in velocity is zero, acceleration is zero, force is zero in equilibrium, but this is not equilibrium. So the velocity, once the object wants to go in a straight line, but something just pulls it back in. Like in Godfather 3, every time it tries to get out, something just pulls it back in. And I wish I could do my Pacino, but I can't. And if you have no idea what that reference was, you need to watch better movies. So if you look at it, I was going in that direction, but now I'm going in that direction. So I'm going to take these two vectors and I'm just going to put them tail to tail. I'm going to try to draw them the same direction. So I'm going to call that V1 and V2. That is horrible. I have to turn my back to you, excuse me. That is still horrible, but I'm going to stop there. So that's V1. Those two are supposed to be in the same direction. I'm assuming your notes will do it better.
You got these from the 6 o'clock and the 3 o'clock and stuff like that?
What I got from here is the fact that when I let go, it goes in a straight line.
Yeah.
Well, it does drop some because there's a force downwards. But that's the direction of velocity as this thing was twirling around.
Mm-hmm.
So if I had something traveling in a circle like this, at this point right here, the velocity is that direction. At this point, the velocity is in that direction. So now what I'm leaning towards is the direction of the change.
Mm-hmm. Oh, yeah. Gotcha.
V2. So if I've done it correctly, this brown arrow for V1 should be the same length and direction as that. As this green one for V1, and the one for V2 should be the same length and direction as the one for V2 here. So if I start here and I move to here, my change is that way. That's the direction of my change in velocity. And since acceleration is directly related to change in velocity, that's also the direction of my acceleration. My acceleration, change in velocity, net force, they're all in the same direction, is towards the middle. So my change in velocity, my acceleration, and my total force are all towards the middle. When I was twirling this around, what force is pulling it towards the middle?
The strain, right?
What's the force?
Tangential? No. Somebody, it begins with a sin.
Center of gravity?
Force. You got F-town. You got a checklist there. It's not buoyant force, so what if you want to do FB down, that's fine for that too.
Could it be tension? This person back there say tension, I ain't say it, he said it.
All right. Yeah, it's tension. Tension's what's holding it in. Tension is that force towards the middle.
I was gonna say, so why did I think,
You said tangential.
I meant to say, I was saying centripetal, somebody.
Yeah, all right. So, forces that are acting towards the center of, if something's traveling in a curve, forces that are acting towards the center are indeed called centripetal forces.
Okay.
In that particular case of this swinging around, it is tension that is the centripetal force.
Okay.
I'm not changing F town or FB town. I guess at this point I've already introduced it. So best friend town, I'm not changing anything to best friend town. Centripetal force is not a new force. It's one of the other ones, or part, or combination thereof. So that centripetal force. Now, I feel like I do need to bring up the other one. Probably in about 5 minutes, it potentially is the last time I'm ever gonna mention this other one. The one that more people use. Incorrectly, usually. First off, pronunciation. Centripetal is the way I pronounce this. I pronounce this one centrifugal. Sometimes it is difficult to understand the distinction if I'm talking quickly or I take after my dad and start slurring words. Nasasan goes, I think it's a more English pronunciation, centripetal and centrifugal. Sometimes I will do that. It's just not naturally how I say it. But I think it's a little bit easier to understand centripetal and centrifugal. However, again, after about 5 minutes or so, I potentially am not mentioning this one again. Let's look at the roots of the words. Center. Seeking. Now we have words in English today besides centripetal. With PET as a major piece of the word, which does mean seeking. Can anyone think of a word that we have with PET in it that means seeking or things coming together?
Is bipedal with a D?
It is.
Okay.
That's more related to the foot.
So what's the question again? I'm sorry.
What word do we have in English that has PET at the heart of it, that deals with things coming together?
Petals? Oh.
I don't think that's the same root. Potentially flower petals, if that's what you were thinking of, because flower petals do sort of
Come together.
connect sort of at the center. I do not know if it's the same root or not.
Mm.
Andre, I was looking at you because I thought you were about to come up with something.
No, I'm thinking
Competition. You have groups come together to compete.
We would have never.
I'm giving you a chance, it's not.
It was good though, because you're right, you're right.
That dramatic pause, sorry if I spoiled it, if someone's about to say this. Or Andre said it under his breath and only 2 people heard it. Over here, we still have center. Fleeing. Now this one, a little bit easier. What English word do we have that has this FUG in it that has something to do with running away?
Fugitive.
Yes.
Wait.
It is centrifugal force. In a centrifugal force, there's this idea that things are trying to get away from the center. There's a common Latin expression, Tempus Fugit, which means time flies. Same read. All right. Now, when is it appropriate to use this word instead of this one? Within the context of this course, probably never after a couple minutes. So let's look at the force diagram. So I had the stopper on a string, and this stopper was moving around. If I do a force diagram of the stopper, we had tension acting in, and then I had the rope here and tension acting out. And then there's a tension at the other end, and then my hand had a tension. That is a centrifugal force. It is a force towards the outside. We're usually concerned with the object that's spinning, so that's the centripetal force. This is the one we care about. The other time that this is appropriate is in what's called a rotating reference frame, and I think Hewitt makes reference to this one. You're in a car going around a curve. Going that way. Your body wants to go in a straight line. Let's see if I can actually draw a straight line. Your body wants to go in a straight line, but the car is sort of cutting you off. It feels like you're getting thrown outwards, but in reality, you just want to go straight and the car is sort of pressing you inwards. Physics should work regardless of your reference frame. So if I do everything, assuming the Earth is still, I can come up with a whole bunch of equations. I can also do a whole bunch of equations that I'm sitting in the car. If I'm sitting in the car, it does feel like there's a force throwing me outwards. Some textbooks will call it a false force, because it's not really a force throwing you outwards, but in the rotating reference frame, in the reference frame of the car, which is going around a curve, that it can also be used. Any comments on this before I erase it and we never speak of it again? All right, enough of that. There is, of course, a formula. Because where would life be without them? Little a sub c, this is for centripetal acceleration. And you probably have some gut instinct what the formula is, even though if I said, hey, write down the formula, a number of you probably would blank, if not all of you. When you're going around, when you're driving in a car and you're taking a curve, so let's say you're going from one road to another, let's ignore the lazy curve of a interstate. You're in a neighborhood and suddenly realize, oh, that's the turn I want to take. What are the two main things that are going to making that turn hard? Difficult to take.
Your speed.
So greater the speed, the harder it is, or the easier it is?
Harder.
So centripetal acceleration is related to force, so you need more force the faster you're going, so put a little v there. And?
How fast you turn the wheel.
Yes, anyone has got a different wording for that?
The radius of the turn.
Yeah. You turn the wheel faster if it's a sharper curve, or sharper turn. So as the radius gets bigger or smaller, it's going to make it harder.
Bigger? If it was bigger, to make it harder?
You're saying the bigger the radius, so it's easier to take that curve than it is to take that curve?
No, it's easier to make the smaller curve.
It's easier to make the smaller curve.
I don't know, what are you asking? So that's kind of-
That's what I'm trying to figure out what you're saying.
It's easier to make the bigger turn.
Yeah, that's my experience. I don't know how you drive
I don't drive fast.
that.
Then you should have experience.
The straighter the road is, the easier it is. And so the nice lazy curve here, where I've got a radius like that, is easier to do than something with a smaller radius. You know, if you think of that as part of a circle.
Okay.
So as R gets bigger, it becomes easier, so R goes on the bottom. I need to make one other adjustment here. I typically in 151 and 251, I go through the derivation of this formula. I will not subject you to that, but if you're interested afterwards, I'll be glad to show it to you. There is a calculus and a non-calculus version of it. But the speed is squared.
Do we need to know it?
You need to know this. You don't need to know the derivation.
Oh, sorry.
So centripetal acceleration is the speed squared, not the velocity squared, but the speed squared divided by the radius of the curve.
Is it not related to how heavy the thing is?
I was
The
thinking
forces, yeah, alright, so the centripetal force is mass times centripetal acceleration. That's where the other part comes into it.
that. Oh,
Technically not how heavy it is, but how massive it is.
okay. Cause when he said the radius part, I'm like, well, what about if it's really big?
Yeah, and that shows up there.
Alrighty then.
Because the greater the mass, the greater the inertia, the greater it just wants to keep going straight. So sometimes you'll see, instead of writing it this way, they'll just write it as mv squared over r.
It's gonna, oh, sorry.
Should we know the force equals M? Should we know the formula on top, that one?
Oh, this one?
Yeah, should we know that one?
Yeah, I mean, it's just mass times that, so somehow you need to understand which one it is. I do want to point out one other thing, and I don't want to make it more confusing, but it might come. This is the vector here. That's the vector there. And suddenly the vector disappeared. Where'd the vector go?
You're a magician.
I just haven't written it yet. So,
That's it?
oh, I'm about to write it.
Oh,
We've talked about I hat and J hat, maybe even K hat at some point. I hat, J hat, you sit down, you define what's the I direction, what's the J direction, and you're good. And then you use those. Have I done R hat yet?
no.
All right, so now I introduce to you a slightly more restrictive unit vector, R hat.
By any chance, what's K hat?
And that's I and J, K is just the other dimension.
Oh.
I guess I potentially haven't talked about it. Okay. It's just the third dimension. So R hat is a unit vector, because of the hat. It's known as the radial unit vector. And whereas I and J, we can always just say, oh, let's make I that way and J that way, or I that way and J that way. R hat is always away from the center. Your only decision is what's the center. So it's a unit vector that points away from the center. Away from the center. So, what is the direction of the centripetal force? Not clockwise, if I heard that correctly.
Away from the center.
What's the direction of the tension on the stopper as I was swinging it around?
Is it towards the ball or no?
So I swing this around, what's the direction of the tension acting on the stopper?
Forward?
Not forward.
Is it towards the center?
It is towards the center.
What did I say, away from the center?
Yes. Somebody did.
It wasn't me.
Sure, okay. We'll blame Andre. You good with that? All right. So I need to somehow, since R hat is away from the center and the centripetal force, centripetal again, center seeking, is towards the center, how would I indicate towards the center? If R hat's away.
Negative R hat?
Yep. And traditionally, you stick the negative up front, and the R hat at the end.
That was good, girl.
So now we got our vector back, life is balanced, and you can sleep tonight.
So all of that will go together?
Yeah, so this is mass times the acceleration and the direction.
I was talking about the FC equals MA.
Yes, that's still, Newton's second law still works, F equals ma. We're talking centripetal now.
Mhm.
And then centripetal acceleration is v squared over r towards the center.
Mhm. Okay.
Now, for the most part, in our problems like the problems dealing with this, we know it's towards the center, and we generally don't write this because we know. But that's just a little bit of formality, because I know how much all of you love the formality of physics. But what I'm sure you're hankering for is a problem with numbers. Table. With a hole in the middle. Side view. I'm gonna call this one mass 1 and mass 2. I assume you've done the centripetal acceleration lab.
Yes.
So let's make this 3 kilograms and make this one 1 kilogram. So if it were just sitting there, if I just set this up, I got a table with a hole in the middle, and got thread running through it, and I just let go, I'm not spinning anything, just let it go, this thing would fall, and that mass 2 would get dragged towards the middle. But we can keep it so that if I get M2 spinning just right, mass 2 will not get any closer to the center. We do an overhead view. So there's the hole in the center, string, and I have mass 2 right here, and then mass 3 is on the other side. And let's have it go counterclockwise. Like that way. So the question, oh, I need to give a radius too, so let's make the radius here